Alright, welcome to section 14.3, change of variables, polar coordinates. So why are we calling this polar coordinates and not cylindrical or spherical coordinates? The reason is we are focusing on the domain. So for a function in 3 dimensions, z equals f of x and y, the domain is the xy plane. So we will look at polar coordinates. So a substitution for the xy, we can use r and theta. So the objective is to write and evaluate double integrals with polar coordinates, and this is going to help us in situations where the shape of the region is circles, cardioids, rose curves, and anything that involves x squared plus y squared, or the square root of x squared plus y squared. Why that? Because we know that r squared equals x squared plus y squared in polar coordinates, so this simplifies quite a bit. So just a reminder, polar coordinates, x equals r cosine theta, y equals r sine theta, and then r squared equals x squared plus y squared, and tan theta equals y over x. So for instance, in the exercise here, if we have a region given like that, we could try to express it in terms of x and y, but you might realize that it could be awfully difficult because there would be some switches between the limits of the region. So we would have to say that if x ranges from -2 to -1, then for any of these x values, y ranges from y ranges from 0 to that circle, which is the square root of x squared by 4 minus x squared. And then from here to there, so from x values from -1 to 1, y would range from the square root of 1 minus x squared to the square root of 4 minus x squared. And finally, in the end, for that last part here, y ranges again from 0 to the square root of 4 minus x squared. So we would have to split this region into 3 sections and add the integrals for each of these subregions. On the other hand, if we are able to change the coordinate system to r and theta, now it's pretty easy. R ranges from 1 to 2, and theta ranges from 0 degrees to 180 degrees, or from 0 to pi, as we will do, of course, since we use radians. So, a little intuitive introduction to how we change from rectangular to polar coordinates. If we have a certain region, and it's a very small region that we will call A, then that area, instead of being x times y, base times height, it's actually in polar coordinate this, so the base is delta r, multiplied by the height. And notice how the height is actually the arc length. So this is the arc length, and the formula for the arc length, S equals r times theta. So if we do base times height on this almost rectangle, if it was super tiny, it would get closer and closer to being a rectangle. The area of that rectangle is going to be delta r times arc length, so delta r times delta theta. And that shows us that instead, if we want to substitute delta x delta y, or dx dy, the substitution will include a multiplication by r. So dx dy will be equal to r dr d theta. This was kind of an introductory explanation, but here is the statement in the form of a theorem. The integral of f in rectangular coordinates over a certain region, so this dA is dx dy, is equal to the double integral of that same function, but this time using polar coordinates, times r dr d theta. So this is the key here. We'll talk about this element again later. It's called the Jacobian. But it's the one thing you have to keep in mind when you substitute, when you change x and y to r and theta, that you don't just change x and y to r and theta, you're also changing dx dy to r times dr d theta. So that's really it for the new material. Now we are going to practice this with examples, and we have the same region as before, so we already figured out the limits of integration. If we if we imagine here it's written dx dy, if we want to change this to polar coordinate, it becomes r times dr d theta, and this means the limits of integration for r are here, and then for theta they will be right there. So r ranges from 1 to 2, and theta ranges from 0 to pi. X squared is r squared cosine squared theta, y is r sine theta. So first thing, we distribute the r, and we get r cubed cosine squared theta plus r squared sine theta, dr d theta. And from here, the process is pretty just formulaic. We're integrating in terms of r, so these are two like power rules, and then we substitute 1 and 2. We get to this point here, and we can, of course, split any integral. We always do it without really thinking. So we're going to have to integrate cosine squared theta, and we have two options for that. The first option is to use Wallace's formula, but instead of integrating from 0 to pi, Wallace's formula goes from 0 to pi over 2, so we need to have a times 2 in front of Wallace's formula. The other option we would have is to substitute, because cosine squared theta is actually equal to 1 plus cosine 2 theta over 2. It's written on the next page. I wrote it on the next page, so you'll see this trigonometric identity again in a few minutes, but you have two options here. That year we chose the option of practicing using Wallace formula, so splitting the integral into 2, we can put the 15 over 4 in front of the integral, use Wallace. Likewise for the second term, the integral of sine theta is of course obvious, so we end up with this integral yielding the answer 15 pi over 8 plus 14 over 3. So some technicalities, but all in all not very difficult. Use polar coordinate to find the volume of the region bounded above by the hemisphere. So here's the entire sphere, but we are only focusing on the hemisphere, and below by the disk in the xy plane. So it's this disk here. So it forms a certain volume that has the shape of maybe a cupcake a little bit. So it's curved here because it follows the sphere, and then it goes down until it reaches the xy plane. So again, there's clearly some circular things about this shape, so maybe substituting to polar coordinates is a good idea. Moreover, since we have 16 minus x squared plus y squared, we're going to want to substitute that with r squared. So this is what it becomes. It becomes 16 minus r squared, and then instead of dx dy, we have r dr d theta, and we need to think about the region here in terms of r and theta. So since we make a full turn, it means that theta ranges from 0 to 2 pi. And as for r, this is a disk with radius 3, so we are integrating from r equals 0 to r equals 3. Here, we can use a u substitution, u equals 16 minus r squared, which is quite convenient because du equals negative 2 r dr, so it's going to absorb this part. And we get that, and from here it's not hard at all. We can integrate in terms of u, substitute. So notice that here we changed back u to 16 minus r squared. If you want to substitute the u value, you have to recalculate what they are. If r equals 0, u equals 16. if r equals 9, if r equals 3, u equals 7. But we can substitute back and get r again. What we obtain is a constant that is 7 to the power of 3 over 2 minus 64. So this is just a number. There are no thetas involved. So integrating that in terms of theta just gives the constant times theta. And then that yields the final answer, negative 2 pi over 3 times the constant I just read, which is approximately equal to 95.2525. That's the volume of the purple region there. Last example in this section, something that you will recognize from AP Calculus BC. Find the area of one petal of the graph of r equals 3 cosine 3 theta. So this is not a question about the volume. However, we can use the volume integral if you want, but just pretend that the height is 1. So we have f of xy equals 1, and that brings the calculation of the volume to be the same as the calculation of the area. So what's difficult in this exercise, I think, is to realize what the limits of integrations are. For what value of theta are we starting here, and then we have to stop when we reach this value of theta. So for what value of theta is r equals 0, and it ends up being negative pi over 6 and pi over 6. Let's try with negative pi over 6. If I plug negative pi over 6 here, I get negative pi over 2, and indeed cosine of negative pi over 2 is 0. So at negative pi over 6 we start, and then we turn until we reach pi over 6, positive pi over 6. What about r? This is difficult again. So for a certain theta between negative pi over 6 and positive pi over 6, so let me choose this angle theta here, which is a little bit more than 0, but not pi over 6, less than pi over 6. What is the range r? R starts at 0 and goes until it hits the petal. So r ranges from 0 to 3 cosine of 3 theta. For another angle theta, let's pick a one that's negative, like this. It also goes from 0 until 3 cosine of 3 theta. So this allows us to put in the limits of integration here, and we have, instead of dx dy, again r dr d theta. So we have to integrate r, it's 1/2 r squared, we substitute, and here again we get cosine squared of something. So it's not cosine squared of theta, so we need to first make a little change of a u substitution. So easy, u equals 3 theta, which gives us another 1/3 when we substitute d theta equals 1/3 du, but altogether we end up with the cosine squared of u du. So one thing that happened here again that we have to be careful of is if we want to use Wallace's formula only works when we integrate from 0 to pi over 2. So we had an integral that went from negative pi over 2 to positive pi over 2, but since it's an even function, it is symmetrical, so we can say that the area is 2 times the integral from 0 to pi over 2. That explains why there's a 3 here, and the 1 over 2 disappeared, because we multiplied by 2 by taking only half of the interval on which we integrate. So we can use Wallace, which was done here to give the answer, or the second option is to use this trigonometric identity, cosine squared of u equals 1 plus cosine of 2u over 2. Note that in AP Calculus BC, when you found such areas, this is the formula you used, which is great. If you think of r being 3 cosine of 3 theta, well, we can see that it brings us straight here. We would have r squared equals 9 cosine squared of 3 theta. So it's exactly here if you start from the calculus BC formula. We again, here the idea is to start maybe one step before in terms of concept when we use multivariable.